Hey folks, well, the idea at this point was to get into the whole program analysis side of things and then spend some more time on code optimization and spend some time on register allocation and then kind of realize that we're down to pretty much our last week and I want at least that last session to do kind of prep and review for the final exam. So we're kind of running out of time here. So this turned into kind of a grab bag of I guess a grab bag summary of things I wish we could have gotten into a little bit deeper. So we'll see how we go here and try and get as best we can for this last chunk of coverage. So I want to spend just a little bit more time talking about the whole program analysis side of things, a little bit more on the code generation, kind of a summary of a few more optimization techniques, a little bit of time on instruction scheduling and on instruction selection, and then a little bit of time looking at how we do the actual register allocation when we get down to the final nuts and bolts stage. So that's more or less what I want to run through here. Let's see. From the whole program analysis side of things, I wanted to bring up the issues that we run into when we get into higher order functions. So our whole program analysis is pretty heavily dependent on the interrelationship of the calls between the different routines in our program. So when we go through and build a call graph to represent which functions can call which other ones, that gets a lot trickier if we can pass functions as parameters and have functions run what was passed to them. Because then essentially anything that could be passed as a parameter is something that we could potentially call. So determining which functions could get called by a higher order function kind of depends on which things could validly be passed. And so just as we kind of ran into with the whole ambiguity side of things, the compiler has to take a kind of conservative view here and say, well, if it could be passed, if it could be passed and called, then I kind of have to assume it does get passed and called. So I have to add it to the call graph. And so this does tend to really complicate the call graphs that we generate and the complexity of them. A couple of other issues that I just wanted to point out. Again, there's the whole OO side of things that we didn't get a lot of time to get into, dealing with, when you're looking at the whole program side, you have to think about object initialization and cleanup, where garbage collection takes place, how you're handling the dynamic binding. Again, we got into a little bit of this from the general perspective and a little bit of it from the C++ side, but there is so much more that you could spend a lot of time on here. In terms of constant values, we looked at the idea of constant folding, but there's so much that can happen in terms of mixing that with function calls or subroutine calls. If you think about when you have a subroutine that returns a constant value, then how do we get that return value mixed into our constant folding, if you like? Or if we've got a function that gets passed constant values, where can we mix those into our constant folding? So recognizing and propagating constant valued function parameters and returns is another thing that's really of interest. There's a lot of data flow analysis techniques beyond the sort of simple iterative ones that we got into. Again, you could spend an entire course quite happily going through looking at more dynamic data flow analysis techniques. And a lot of those go into getting a more accurate, a more minimalist but fast computation of the dominance frontiers that we looked at. Once we go through all this, we still have issues that we haven't really addressed from the code generation side. Again, we're going through and saying you've got this, let's say we've got a single static assignment form for our representation, and we're trying to transform that into our target language. And maybe we've actually gone through and dealt with the issues in terms of resolving conflicting variable names and that sort of thing. So we've got all of that resolved, but we still have to transform this into a language, into our target language. So typically, you've got an entire infrastructure there to support the individual translation steps that you're interested in. So you have to know about your target language and your target architecture, what are the naming schemes for the registers that are available? What kind of groupings of registers do you have? Do you have one set of general purpose registers and one set of floating point registers? Do you have a set of address registers? Are there special groups of registers? How many of them are there? How big are they? What are the naming schemes for them? What are the memory alignment rules? What are the sizes for the different data types in your target architecture? What are the procedure call and return conventions that are in use? And then all of the details on the specific types of instructions that are available to you. In your target language, what are the patterns for source and destination operands? Is it for the different instructions? Are they 1, 2, 3, 4 operands? What does the syntax look like? What are the instruction names? So you've got all of this data that needs to be stored when it comes time to mapping our SSA instructions into our target language instructions. Beyond that, you've got to pick the actual specific set of instructions you're going to use and what order you're going to run them in. So we talked earlier about the idea of having this sort of partial ordering of the instructions, where we know that this instruction has to be before these two, and this instruction has to be before these three, and this instruction has to come after these other three. So you've got some kind of a partial ordering, but you can map any ordering that you like that fits that, any sequence of instructions you like that fits that. So we'll talk a little bit about the instruction selection and instruction scheduling, but they're all computationally difficult problems. And then the register allocation side, trying to map this sort of SSA style of naming that we came up with to an actual physical set of registers when we get there, is going to be another issue that we have to deal with. So in terms of a couple of the optimization techniques that we didn't get much of a chance to look at, there are a few things that are certainly worthwhile from a compiler point of view, going through and getting rid of the useless things that are in there. We looked at getting rid of data values that aren't used anymore, but there are so many things beyond that. We can go through, and one of the things that you might do is kind of like a garbage collection approach, where what we want to do is figure out which expressions, if you like, are actually useful, which values are actually useful, which chunks of code are actually useful. So we can go through and mark all of our values as useless in the beginning. And then we're going to go through and see if we can identify which ones are actually used. So on a first pass, we'll go through and say it's useful if it's related to input or output, if it affects a return value, or if it affects values that are stored kind of outside the block that we're interested in right now, or the routine that we're interested in right now. So if it affects something external, then we don't know how that fits into the greater scheme, so we better treat it as useful, right? Better treat that as something that we have to hang on to. So then you've got this set of things that you've decided, okay, these are useful bits in our code. Then we'll trace backwards from those and look at where their definitions came from, which values did they use, which expressions did they use, and continue tracing backwards from there. So you get this kind of reverse tree working back from the useful values. And everything that it depends on, you flag as, oh, okay, I need that because I need it to compute this other thing. And you keep working backwards and marking off all these things as, oh, I need that, oh, I need that, oh, I need that. And once you're done, you can go through and see if there's anything out there that is still marked as useless. And at that point you go, well, I'm not actually using this for anything, so let's get rid of it. So you can go through and try and eliminate code that effectively serves no useful purpose. Then we can do a similar sort of thing with code structures, where we go through and try and identify unreachable code. If you've got an unconditional branch someplace where you jump to the top of a loop, for instance, if there's a chunk of code there, like right after the jump, but before any kind of a label, then that's unreachable code. Right? The nearest place you can get to is the next label after that unconditional jump. So again, you can identify this as unreachable code and get rid of it. Right? It doesn't serve any useful purpose. If there are blocks, you can get rid of those. The programmers included an if case or an else case that has nothing in it. Serves no purpose. We can get rid of it. If there are redundant blocks, we can get rid of those. So you're going through trying to identify all the different chunks of code that you might manage to get rid of. All right. Then we get into our instruction selection side of things, where, again, we need to come up with some kind of a mapping from our SSA to our actual target language. So during that tree walk process that we were discussing, we need to go through and see if we can map our names to physical storage, figure out what loads and stores we need, match our SSA operations and instructions to our target language operations and instructions. One of the things that we can do is say, well, can we recognize, again, if we think of our SSA as representing this sort of tree-like structure, can I perform pattern matching on the subtrees? This is what a subtree looks like for an if statement, for instance. This is what a subtree looks like for one of our function calls. This is what a subtree looks like for a whatever. This is what a subtree looks like for raised to the power of, some power of 2, raised to a power of 2. Are there patterns in our subtrees that we can look for where we can say, that pattern matches up to this pattern in our target language? And so if we can come up with patterns that we can recognize, patterns of subtrees that we can recognize, and patterns that we can translate them to, then what we want to do is kind of work through our tree and apply all of these patterns across the different subtrees, trying to cover our whole SSA tree so that we've got a way to translate each individual piece of it. So if you can come up with this set of pattern matching rules and then the set of translation rules for each individual pattern, then we can go through and translate the entire thing using a process like this. Now, we're looking for some kind of optimal set of pattern matches where we get the best rewrites possible to produce good target language code. But this is one of the ideas for going through and trying to say, well, how can we do this effectively? You might follow that up and say, okay, this overall pattern matching approach might work well for getting a valid translation, but maybe it's not the best possible translation. So maybe we follow it up with some kind of peephole optimization where we create this little sliding window that just looks at a couple of instructions in a row at a time and sees if we can take those couple of instructions and rewrite them to be something that has equivalent behavior but is more effective or more efficient or whatever the idea might be. So again, there are a variety of different techniques that we could spend quite a bit of time on if we had the time and opportunity here. Then we get back to the instruction scheduling side of things that, again, we mentioned a little earlier. We've got this partial ordering on the instructions where we know that certain instructions have to come before certain others, but that still leaves us a lot of leeway in specifically what exact order we put them in. Now, the target architecture that we're aiming at might do its best to kind of overlap instruction execution where it can, do things in parallel where it can, pipeline fetching of operands, pipeline fetching of instructions. So while it's executing this instruction, it's doing as much as it can to get ready for instructions that are coming up. So ideally, our instruction scheduler, right, whatever's picking the precise sequence of instructions we're working on, wants to work to give the target architecture as much flexibility as possible to go ahead and perform that sort of look ahead, that fetching ahead, the parallelization where it can. So we're trying to set things up so that we minimize any cases where the architecture has to say, rats, I have to sit and wait for this value before I can use it and perform, this next set of instructions. Or, geez, I have to flush out my pipeline because the branch that was taken wasn't the one that I was anticipating, and the instructions that I've got to get aren't actually in the queue. So we're trying to set up our instruction scheduling to minimize that kind of impact on the eventual target architecture. So once again, we could spend a huge amount of time going into some really interesting problems in terms of the instruction scheduling. One of the things that we can do with that is, again, start off with our sort of partial ordering for our little basic blocks, and then perhaps go through something like we did with value numbering, where we said, okay, well, perhaps when I'm looking at my scheduling, if I've got a sequence of steps that are a sequence of blocks that are more or less linear and this nice linear path, then I can try and apply my instruction scheduling techniques across those, try and apply my ordering across those and do a little bit of optimization there. So a lot of the ideas that we looked at for basic blocks and extended basic blocks for our value numbering, we can try and apply similar techniques for our instruction scheduling. Then we get to the fun and joy of register allocation. So here we're going through and trying to take this set of names that we came up with for our SSA approach and map it to the actual number of registers that are available on the target architecture. So, maybe our SSA came up and said, we need 73 registers, and in fact we only have 24 or 32 or 12 or whatever it might be. So somehow we have to make that mapping where we're going to say, okay, only some of these things can be in registers at any given point in time. The rest of them have to live in memory, and at some point we'll need to move them into a register and use them, and at some point they're probably going to wind up going back to memory. So we need this approach to figure out what's going to be in registers when, and what's going to be in which specific registers when. So doing this effectively is going to have a huge impact on performance, right? The operations to memory tend to be much slower than the operations on registers, and so the amount of time we spend moving things back and forth to memory is going to have a big impact on the runtime that we wind up with. So our register allocator is going to take this code that we've written that uses n registers, however many we actually used in our SSA, and it's going to rewrite it to use the correct number as limited by the target architecture. So it's got to go through and figure out which values are safe to put in registers and when, so dealing with the ambiguity issues. And it's also trying to pick the ones that are going to give us the greatest benefits, right? Which ones minimize the number of times we're going back and forth to memory. And again, this can get more complicated depending on the architecture. If it's got multiple different pools of registers with different characteristics, then we have to take those into account as well. As we get a little bit of commentary from our cat. Here, go flee. So the allocator might try and take this and split the task into a couple of different parts. So the first part, we might simply try and get that set of n names from our SSA and cut it down to the right number of names. So if we wound up with 37 names originally and we have to get it down to 16 for the number of actual available registers, then maybe we do that first, come up with our 16 names and try and reorganize things to fit in 16 names. And then once we've done that, we can take the 16 names that we've got and figure out when those 16 names are mapped to which specific registers. So you've got this allocation part and then this assignment or mapping part. And those are two, again, if we treat those as two separate problems, we can simplify each one a little bit. The allocation is by far the more challenging problem. You can usually come up with a polytime approach for the assignment or the mapping, but that allocation side is one of our NP-complete problems. All right. For the allocation and assignment problems, we can, again, split this into layers. We can look at it in a sort of local basic block level and then start looking at, okay, well, what happens if we've got a collection of blocks and we've got to coordinate across them? So on the local side, let's say we've got M registers available, and we're going to have to move some stuff back and forth to memory most likely if the number of names that we've got is bigger than M, then we're going to have to do some moving back and forth. And so we're going to need a couple of registers or a few registers set aside to do that moving back and forth, right, for the values that we have to grab from memory, use, and put back. So out of our M available registers, we'll set aside a few of them, so we'll call that K as the registers we've got to set aside. for kind of overhead and manipulation as we're moving things around. Then we can take a kind of top-down approach or a bottom-up approach to how we'll actually match our names up with our registers. Top-down approach basically just says we'll take the ones that we use the most and stick those in registers. So you take your m minus k, however many registers that gives you for your general data, count up how many times each variable is used in the block, and the most frequent ones you put in those registers. So you pick the m minus k variables that are used the most often, stick those in the registers. Everything else you just say we'll just move back and forth. So that's a nice straightforward approach, right? You can do your count pretty quickly. Bottom-up approach tries to take a little bit more of a takes a little bit more computational a bit more of a computational challenge to figure out better which values we can move around and in what order. So things will be moving back and forth. It won't be this one set of things that we're going to keep in the registers and a bunch of other stuff that we'll just kind of grab, use, put back. What we'll do is have this kind of sliding collection, more like a paging or caching approach, where the things that we're using right now or the things that we're going to need in the near future, we try and have in registers, and the stuff that we're not going to need for a while, we let slip back into memory. So we go through our code and put together a sequence that shows us when in our instruction sequence different values are used. We fill the available registers in the sequence, and then as we're going through, once we need a value that's not in a register right now, then out of the ones that are currently in registers, we look at the one that's not going to be used for the longest amount of time in the future, so the one that we won't need for the furthest distance, dump that one, spill it out to memory, and use its register for the new value that we need to bring in. So you've got this constant approach where you're kind of looking ahead at when you're going to need stuff next. And when you run into a situation where your register set is full and you need something new, then dump something, spill something out to memory, and look ahead or bring something else in. So you've got this kind of local approach that can be done reasonably effectively. It gets a little trickier when you're trying to orchestrate things across all sorts of different blocks in a subroutine, right? Because now we've got not just these kind of spills to memory that are happening within a block, but we've got them across all sorts of blocks, and we're trying to coordinate them. And you've got the usual issues of, you can follow multiple different paths to get to a particular block, and depending on which path you choose, then one set of mappings of names to registers might be better than another. And so you're trying to come up with cost-benefit analysis based on how much you're saving in terms of how frequently you expect different combination of blocks to run in sequence. So it is a much more challenging problem. So we will often wind up looking at things like a live range, where you go and take a look at sets of things that are often used together across a sequence of blocks. So a set of expressions whose results are used over and over again across a sequence of blocks. So if you have this set of things, these 3 or 4 values or these 5 or 10 values tend to get used together a lot across this particular sequence of blocks, then we'll try and keep that set of things in registers as much as possible, or see if we can. And you get this idea of this sort of competing groups of values or competing sets of values that we're trying to keep together in registers as we go trundling along. So there are, again, all sorts of really interesting approaches and algorithms for trying to do effective allocation here. One of the most interesting ones, well, I guess I'm biased here, I like graph coloring. So graph coloring algorithms work off the idea that if you've got some graph with a bunch of nodes, we're going to try and color the nodes, and the nodes are all connected by edges, and we don't want 2 nodes that are connected by an edge to have the same color. So the idea is we can k-color a graph if we can assign colors to all the nodes so that no 2 like-colored nodes share an edge. So what we're going to try and do here is use k as the number of registers that we need, and use edges as indicating that two different values need to be in registers at the same time. So essentially they can't share a register. So the notion would be we'd have this graph that represents all the different values that we're playing with, edges between our values if we might need to have them in registers at the same time. And we're going to try and come up with a k coloring so that means that each color corresponds to a register, if you like, so which things are in registers at any given time. And if we can come up with a k coloring, then we can come up with a way to have everything in registers and nothing conflicting in the time period that we're interested in. So these interference graphs are the kinds of graphs that we're talking about. So it is an interesting approach where we model our problem, see if we can k-color it, right? See if we can color it with the number of registers that we actually have available to us. And if so, then we're fine. But if not, then we've got to pick some of those values and say, well, we can't meet all of the constraints of this graph, so some of these things are going to have to be dumped to memory and brought back in as we need them. So in that case, we'll be looking at sort of low-cost spills to try and achieve the coloring that we want. So there are, again, some really interesting problems related to the kinds of things that we're trying to do in our optimization for all the different aspects of our compiler systems. Let's see. I think that was pretty much the rundown on things that I wish we'd gotten to. What we'll do in the next session is do kind of a wrap-up of the course, maybe some prep for the final exam, and see how we go. I will leave it there for now.